I want to talk about one of the investigative tasks, and this year this is not a type of problem that will be on the AP exam. However, it, parts of it are definitely uh, possible. We're accountable for understanding the statistics in this problem. So I want to go through here. I'm going to make this into two videos, one for part A, and then the second part of this problem, which I think will provide us some good review and maybe even a little bit of new learning. So this question, you can read through the description here a little bit for yourself, but they are comparing, um, you're comparing the scores, pre and post test scores, at two different types of schools. You're comparing it at a what's called a magnet school, and then you're also comparing it at the original school. So the what we actually have uh, two sets of data here. I'm going to scroll down so you can see it. So the table, it says right here, so the table below shows the scores in the same science pretest and the same science post-test for 20 students. Of the 20 students, 8 were randomly selected from the magnet school and 12 were randomly selected from those who applied to attend the magnet school but who were not selected and then attended the original school. So you have two groups of students here. They're different students. These 8 students at the magnet school are not the same any of the same students that went to the original school. So we have two groups of students that we're interested in, and then we have data on those students. So for the 8 students at the magnet school, this is the data we have. Here's the 8 pre-test scores. Here's the 8 post-test scores on this science curriculum. And then this is the difference in those scores, post-test minus pre-test. So if you look at like student 1 here at the magnet school, they made a 17-point increase from pre-test to post-test, so that was good. Unfortunately for student number 3, they actually went down a little bit, so maybe this didn't quite work for them, and we see one person with a gain of 25 points. So then these statistics over here, let's make sure we understand what these are saying. This is the average of the sample of 8 students from the magnet school, their average pretest score, and the standard deviation of these 8 scores. Same thing over here, except this is the average of the post-test and standard deviation of the post-test sample scores. And then this is the average difference in those scores, post-test minus pretest, and the standard deviation of those differences in these scores. We have the same data for the original school, but this time it's for 12 students. Same sort of idea, same interpretation. So we would like to, we're going to analyze these and we're going to do a little comparison here in a second. But these are your pre-test scores for the 12 kids. These are the post-test scores for the 12 kids. There's their average on the post-test, the sample mean, the average of these 12 students on the pre-test, sample standard deviation. So the standard deviation of the sample pre-test scores for these 12 students. And then we have the sample standard deviation of the post-test scores for these 12 students. Finally, we have the differences over here. So we see what the differences are. Again, like this means that student 5, I believe, had a 10-point increase, but student 1 had lost 3 points between the pre-test and the post-test. And then we have the average change in post-test minus pre-test, the average difference here, and the standard deviation of these scores. So just from a understanding, data comparison is an important concept, right? So if we look at these two sets of data, the difference is here and the difference is here. We're really trying to figure out, did this magnet school have really any effect on these scores is really what we're talking about. Was there a difference? It was significant difference in the average change in these scores. So that's what we're going to be looking at here in a second. But you could see, a couple things stand out right away, right? That for the magnet school students, they had an 11.75 average increase in their score. However, they were more variable. They had a higher standard deviation in those changes, those differences, than over here in the original school, where they were less variable. However, they didn't have, on average, as high of an increase. So the question is this significant or not? Is this difference between these averages we have, these average changes, is it significant? Did the magnet school make a significant difference in the post-test, pre-test differences we saw. So here's our question. Perform a test to determine whether students who attend the magnet school demonstrate a significantly higher mean difference in test scores post-test minus pre-test than students who applied to attend the magnet school but who were not selected and then just attended the original school. So what do we have here? We have two things we're interested in, two parameters of interest to us. Okay. We have, let's say, we'll call this is about an average. So this is referring to mean. So we'll say mu1. Okay, what are we talking about? We're talking about the true mean difference. And we know the order, post minus pretest. True mean difference, post-test minus pretest score in the scores for students at the magnet school. And then mu2, the other parameter of interest to us, is the same thing here, except this is for the original school. So the true mean difference, and we're going to go in the order, post minus pre, in the scores for students at the original school. Okay, we are going to do a hypothesis test. So we need to set a significance level. Let's set this as a 5% significance level. We're talking about test scores here. This is not medical or anything like that. So we don't really need to go 1%. 10% would be okay too, but 5% is typical. So our significance level. So what's our hypotheses? So our null hypothesis. Okay, so when they give these tests, they're trying to determine if there's a difference or not, right? So initially when they go into this, their expectation is that there is no difference. So the true difference, we would expect that the true difference is 0. And again, you could write it like this, which I think is good for statistics, or you could write it like this. The alternative, so what does it say? Right here, to demonstrate, so students who attend the magnet school demonstrate a significantly higher mean difference. So the magnet school average was mu1. So what we want to know is this difference that we see between these two schools, the averages of these two schools, greater than 0. In other words, is the average difference for the magnet school greater than the average difference for the original school. Okay, so to run this hypothesis test, we need to check conditions, and we need to do that for both populations. So let's take a look here and how we're going to do that. So we have our conditions. Make a little chart to compare both populations here. So we have our original, and we have our magnet. Okay. Okay, let's go back to the problem. Did it say anything about random samples? Bingo, right here. Randomly selected. We had 8 were randomly selected and 12 were randomly selected. So we have a random sample here. That's good. And we have a random sample here. Here. That's good. Okay, so we have our random checks done. That's the first part, right? Oh, number 2. Okay, number 2 is going to be the normal check. I'm going to skip that just for a second. Number 3 is independence. So our sample sizes. So I'm going to start jotting down a little bit of our sample data, right? So what's some of our sample data? So sample data we have. Okay, so let's see. So N1 for the magnet school was 8. N2 for the original school was 12. So when we look at those, we need to check that we think that these students, that their scores and their differences are independent. So for N1 equals 8. All right, so you're talking about school. Are there reasonably less than is 8% reasonably less than 10% of those students? Probably. So 8 is reasonably less than 10% of the population of students. Other thing we need, I want you to add to that is that means that there are probably more than 80 students in the school, right? Okay, that's the independence there. And then over here, N2 is 12, so that likely means, is it reasonable to believe that there might be, more than 120? Probably. So N2 equals 12. It's probably less than 10% of the population. That means there's probably more than 120 students at that school. So it's just reasonable. We should be okay feeling like they are independent. So we shouldn't worry too much about, how are their scores related, like having same family members or something like that, or having study buddies and things along those lines. So I skipped this for a second because this is your normal check. So we have to do some normal checks for each, right? So here's the deal. First, if you go to our problem, you always look, does it say anything about the populations being normal? So if I do a quick scan here, I don't believe we saw anything about populations of these changes anywhere in there about them being normal. So what does that mean? Okay, so that means we can't just say, okay, well, we have a normal population, so we're fine. So then we look at our sample sizes. So our sample sizes were 8 and 12. They're definitely not bigger than 30, so we can't use the central limit theorem. So what does that mean? It means we have to check a dot plot of each of these differences. Okay, so we need to check a dot plot of these differences right here, and a dot plot of these differences down here for each sample to see if it's reasonable to believe they came from a normal population. I'm going to do that here and then copy it over, but we should do that and we got to we'll label those here in a second. So this is a dot plot of differences at the magnet school. Let's do a quick little dot plot here of these differences. Okay, so we got to go, here's 0. -2 would be somewhere down here. This would be like -2. And then 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So maybe these are by 26. 20 somewhere out here. It's 10, 12, 14, 16, 18. Here's 20. So we'd have one at 20, -2, 17. So here's 17's over here. We got one at 1. 25. 25 is out here. We got 6. We got 12. We got 15. Looks pretty symmetric, right? There's no big clustering anywhere, pretty uniformly distributed. This could have possibly come from a normal population. So because we see no clustering, we'll write that in a second, no clustering, no multiple peaks, it's pretty symmetric. This is reasonable to believe these differences came from a normal population. And then let's take a peek at this one. So let's look at what our dot plot could look like here. So this would be a dot plot of the differences at the original school. So let's see. Okay, this one, let's put 0 in here somewhere. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's 5, -1, 2, 3, -3. So -3, you got 1 there. You got 1 at 9. You got 1 at 2. 1 at -1. Got 1 at 10. Got 1 at 2. 4. Another 1 at 4. Another 1 at. Then you got 1 at 7. 0. And 1 and 1. Okay, that's not bad. Not bad. Maybe a little skewed this way to the right, little gap right here. But overall, this thing is pretty symmetric with one peak in the middle. it's reasonable to believe that these came from a normal population. So what we would have here in our boxes, I'm going to save a second and not draw it, is you would put your dot plots in here and you would explain how you use them. So for both of these, since both dot plots have no outliers, no multiple peaks. Well, come over here for a second. Multiple peaks, fairly symmetric. Okay, that's this all together for both of these populations, or for both of these samples. The populations are reasonably normal, or could be. They could have came. That what we're saying. Populations are reasonable to believe they're reasonably normal. So, for all we know, that it could be possible. That's what we care about. Okay, so at this point, we've checked our conditions. They all check off. The last one we would add in here, we're talking about means, and that one would be, do we know the standard deviations of each of these populations? Fourth one, since standard deviation of the differences in the scores for the magnet school population and the sigma 2, which is the standard deviation of the differences in the scores for the original school, are unknown. We're going to use some sort of t. So we're going to use some sort of t distribution. So this test, all of these check off. We got all of this stuff here. We use a 2 sample t-test for the difference of the mean. So these differences right here. And we're going to get that off our calculator in here a second. So we got our sample data. We got to go to our tables here for a minute and pull that off. So our sample data should be from right here. So this stuff right here, this is X bar 1 and S1. And this stuff here is X bar 2 and S2. So X bar 1 is 11.75. So we would say X bar 1 is 11.75. S1 was 9.407. X bar for 2, I believe that was exactly 3. Let's just take 3, and then 3.977 for the standard deviation. So 3, and then S2, 3.907. Let me just double check that. Or 3.977. Good thing I checked that. Oop. That thing right there should be a 7. Okay. All right, there's your data. So at this point, we could use a 2 sample t-test for mean. So we can go to our calculator and enter this stuff in, and hopefully draw our conclusions. So let's go to our calculator. We would pick stat test 2 sample t-test, which you can also just write on your question to show complete understanding, which is fine. We have statistics. X bar 1 was 11.75. Its standard deviation was 9.07 or 9.407. There were 8 students in the magnet school. Then we had 3 and 3.977. So 3.977. Sample size over there was 12. What was our alternative? Our alternative was we had a greater than, so mu1 was greater than mu2. So we'll pick greater than over here. So we got to come down here. Pick greater than. We are not doing pooled. And we hit calculate. So we see what our t-statistic is. We've already reported this stuff, the standard deviations and means. We need this data right here to make our conclusion. So we're going to take that. Got our degrees of freedom you have to state because it is a t-test. So we have this thing, and we're going to use this information. We got our test statistic now. Our test statistic is this t. And we have our p-value, which is 0.0177. So, and degrees of freedom. So our conclusion should be comparing this to our p-value, or comparing the p-value to our significance level. So what was our significance level we set for us? We set a 0.05, 5% significance level. So this is just a little under 2%. So since our p-value of 0.0177 is less than 0.05, we reject the null hypothesis that there is no difference in the mean change or difference between the schools. Pause for a second and digest that. You are throwing that out. That means the null hypothesis, you do not support that. You do not support. So we would say that, like no support for the null hypothesis. Okay. Logically, why is that? Our sample data occurred with a low probability. So like this difference, look at this. Look at this difference. If you look at the average change over here for magnet school versus the average change in the original school, whoop, this thing just wants to keep drawing. There's almost an 8-point difference here. So this is a significant difference according to our statistics. So we reject the null hypothesis. There's no support for it. The evidence or the data suggest that students attending the magnet school have a larger average difference in their scores. So the magnet school made a difference in how the students did on this test. So I will make a second video for the remaining part of this, which involves some linear regression, which is a good review. This problem is near and dear to my heart since this is the year I took the AP Stats test, and I actually remember this. So hopefully you're all doing well.